Power of the z-test for the mean, section 8.1. Example 1, consider again the following hypothesis test for a sample of n equal 15 patients. The mean creatine level, x bar, 1.4 milligrams per deciliter with known standard deviation, sigma 0.5, with 95% confidence. We want to test H naught, mu equal 1.0 milligrams per deciliter. Patient creatine level is the same as that of the general population versus HA, mu not equal to 1.0 milligrams per deciliter. Patient creatine level is different than that of the general population. Again, assume creatine level is normally distributed. And we want to find, part A, we want to find beta, the probability of a type 2 error if the actual patient creatine level is 1.3 milligrams per deciliter. So, so in order to compute beta, we need a specific value of mu under the alternative hypothesis. So, depending on which number we pick, we'll get a different value for beta. But you could pick any number other than 1.0 and for mu, and then find a probability of type 2 error if that value was the true value for mu. So beta is the probability of failing to reject H naught if H naught is false. So it's the probability that z sub 1 minus alpha over 2 is less than x bar minus mu naught greater than over sigma, less than z sub 1 minus alpha over 2 if mu in fact is equal to 1.3. So z sub 1 minus alpha over 2, we can look that up in the table. I think we looked that up before. It's 1.96 for 95% confident, and mu naught is 1.0, n is square root of 15, and sigma is 0.5. So okay, so we're not going to plug in a number for x bar because because x bar, we're treating x bar as a random variable in this in order to compute the probability of a type 2 error, because the sample mean can vary from one sample to another. Okay, so we want to solve for x bar here, and so we want to multiply both sides by 0.5, divide by both sides by square root of 15, and that'll give us x bar minus 1.0 is between negative 0.253 and positive 0.253, and then we can add 1.0 to all sides of the inequality and get x bar is between probability x bar is between 0.747 and 1.253, and now we want to plug in the number for mu. We're saying want the probability if mu is equal to 1.3. So we can make z-scores, make these numbers here into z-scores by subtracting the mean and multiplying by the square root of n and dividing by the standard deviation. So this will be a probability that z is between 0.747 minus 1.3 times square root of 15 over 0.5 and 1.253 minus 1.3 times square root of 15 over 0.5. If you do the computation, that's the probability that z is between negative 4.28 and negative 0.36. And because our table is not set up with negative probabilities and negative z-scores rather, but we can, because of symmetry, this is going to be the same probability as the probability of z between a positive 0.36 and a positive 4.28. Look up both numbers in the table and subtract. So for 4.28, it's actually bigger than anything in the table, so I estimate it to be approximately 0.5. 0.5 minus 0.1406 is 0.3594. So the probability of a type 2 error, beta, is assuming that the actual population mean is 1.3, would be about 36% chance of a type 2 error. And then we can compute the power of the test. The power is 1 minus beta. 1 minus 0.3594 is about 0.6406. Just a reminder that type 2 errors and powers are rarely computed because we don't know the actual population parameter, and therefore our calculations are hypothetical. In this example, we can only say that if the mean creatine level in the entire patient population is 1.3 milligrams per deciliter, then the probability of a type 2 error is 0.3594 and the power is 0.6406. And that concludes this presentation.